Welcome. So what we found is a novel class of attacks against Intel BootGuard. Intel BootGuard is basically the firmware verification and measurement a feature that Intel offers to protect against malicious firmware or other kinds of hardware attacks on a firmware system. So I'm Peter Bosch. Well, this is actually my first security-related research I've done. Mostly been spending the last few years reverse engineering things when I wanted to figure out more about them. And when I got a new laptop and heard I couldn't put core boot on it because of BootGuard, I really wanted to know how that worked and if there was some way to get around it. So that's how I found this. And I'll just have Trammell introduce himself.
Okay. Well, looks like we're having some HDMI issues. So I'm Trammell Hudson, and I've been doing hardware and firmware security research for the past few years, both on the offensive and the defensive side of things, from the Thunderstrike work back a few years ago to the Heads and Linux Boot firmware projects. And we're very focused on how can we protect against hardware and firmware threats. And it's not just a research problem. This is an industry-wide problem. Folks like Intel are also very concerned about how to protect systems from these sorts of attacks. Vincent Zimmer is the head of the UEFI project at Intel, and he gave a talk at the Intel Developer Forum where he laid out a lot of the attacks on the platform, from different sort of rootkits and malware in the boot ROMs to things, malicious devices. And he presented Intel's solution to this, something called BootGuard, that's a fully verified boot sequence that moves the root of trust into hardware and does policy enforcement through that hardware implementation. Unfortunately, they have not released anything without NDAs, so there's no real public documentation about how it works, which means the best documentation right now are presentations like Alex Mitrofsoff's Who Watches the BIOS Watchers, that lays out how BootGuard is organized, what the various structures are, and how the chain of trust works. And chain of trust is an important term that we're going to be talking a lot about in this presentation. So as a quick, very simplified overview, the BootGuard chain of trust starts inside the Intel Management Engine's boot ROM, which is on die and immutable in the hardware. It has enough smarts to verify a signature on the IME region in the SPI flash on the main board, which is then able to start the x86, which runs Intel-signed microcode, which is able to validate Intel's signature on the authenticated code module also in the SPI flash. And these are all signed by Intel's private key and verified with keys that are fixed in the hardware. The authenticated code module is transferred a set of OEM keys that are fused by the manufacturer during manufacturing time and are then used to validate the reset vector and the SPI flash, the reset vector and the PEI region in the SPI flash, which then validates signatures on the Dixie region in the SPI flash, which can then validate the bootloader, which can then validate the OS kernel. And these are all signed by the independent BIOS vendors or the OEMs or the legacy operating system manufacturers. And this is wonderful from a security perspective because it does ensure that if implemented correctly, no unauthorized code will run during the boot process. But as Peter mentioned, he wanted to run core boot. And other people in the free software community have complained about this, such as Matthew Garrett, who pointed out that while this is great for security, this makes a trade-off against user freedom, that it sort of violates the spirit of free software if we can't put our own firmware onto our own machines. But as he points out, Intel should be congratulated for building a system that does give us a hardware root of trust, because it does mean that very complex attacks are now in scope. Things like evil maid attacks that used to be considered out of scope and too hard to defend against, or attacks that required physical access to internal hardware to install hardware implants or other devices, used to be considered just game over from security. But with BootGuard, these attacks are supposed to be protected against, and that's actually a good thing if we can have some user freedom to go along with it. And the key management and the cryptography does seem to be fairly sound, but there have been some attacks against BootGuard. And they're not against the algorithm itself, they're against the implementation and typically against the OEM components of that implementation. One of the most glaring problems right now is a lot of OEMs are not even turning on BootGuard. They're leaving the machines with the OEM keys unset, which means that malware could potentially set those keys and create rootkits that could not be removed by anyone on the machine. Alex Ermolov presented at Zero Nights, where they found quite a few vendors were not bothering to enable it. Other OEM implementations have made some poor choices, such as what Embeddy found, which is that the BootGuard checks would set a global variable and then depended on code in the Dixie region to check that variable and enforce policy. But you can't enforce policy from something that is being checked by it, because if the attacker can remove those checks, then there's no code that actually ensures the validation is correct. There have been other sort of bad design decisions that folks have found, such as Alex Matrosov, who realized that when Windows 10 does its update, it has a way to turn off BootGuard, which means that the hardware root of trust is no longer rooted in hardware, that it's only a software bit away from being disabled. So this also indicates the biggest problem with the chain of trust is it's not defense in depth. It means that every link in the chain has to do the right thing, has to implement security correctly, or everything after that in the chain can be compromised. An example of where this can take effect is something like the Positive Technologies attack on BootGuard, attack on the ME, that once they were able to get code execution in the ME, they're able to pass their own OEM keys up to the ACM and pretend that that they've signed the firmware. There have also been some vendors where parts of the firmware have not been included in the BootGuard hashes. Both Lenovo and also Intel made the mistake in some of the reference code. So when I found these two vulnerabilities, it wasn't a complex analysis of algorithms. It literally was loading the firmware into the UEFI tool program, which helpfully color codes the parts that are BootGuard protected by Intel's hashes, the parts that are protected by the OEM piece, in this case the Phoenix hash, and then a bunch of firmware volumes that are just completely unsigned and unhashed. So any executable code in there basically gives an ability to bypass BootGuard. Most of these attacks would be detected by a measured boot mode. So where these firmware volumes are hashed into the TPM, and the PCRs would reflect the actual values that were in the ROM. So even if an attacker were able to modify them and get code execution, they would not be able to extract, say, a TPM sealed secret, because the code that is executed is the same that is measured into the hash. But what if there's some sleight of hand where it's possible to change that code after the validation and the verification, but before the execution? And to talk more about that, I'll hand it back over to Peter.
Yeah, So yeah, Intel did actually think about this in the design of BootGuard. As Trammell mentioned before, hardware attacks really are in their threat model. So let's see. When you look at the manual that vendors get for configuring their BIOSes, there's this little thing in there that says protect BIOS environment, and it basically allows vendors to configure the ACM, the Authenticated Code Module, first part of BootGuard, to configure the CPU in what's known as cache as RAM mode, and put the entire first part of the firmware inside the last level cache. So any attacks on the hardware can't touch it anymore. No DMA attacks, no attacks on the flash itself. So this shows that they did actually think about trying to prevent this. What actually is cache as RAM? Cache as RAM is needed because in modern systems you don't immediately have your DDR memory working when the processor starts up. There's a lot of configuration that needs to be done in order to get there, and that happens after this stage. And you want to make sure that the code that does that is actually verified. So you need a different way of safeguarding your code, and they reuse the cache to do that by putting it in write-back mode, writing the stuff in there, and then you can basically use it as RAM. So this is basically what we would do if we wanted to prevent against the check time of use attack. We'd copy whatever we need to verify into a safe area, and then we verify it, and no one can touch it, so it's safe. Because there's no RAM, you'd use cache as RAM. It looks something like this, where it's on separate addresses, and so it's safe. But you need to copy it. That's slow. And then you need to verify it again. So you're basically reading it twice. So Intel came up with a smarter way to do this. Skylake CPUs and newer have a no evict mode of the cache, which means that not just can you use it as RAM, you can actually tell it never to evict a line, even if it's not dirty. So you don't need to copy it anymore. You can just have your ROM with your initial boot block, and do your hash verification on that. When you do that, you're reading it, so it's cached. And because the cache isn't allowed to evict anything, it will stay there and it's safe. Well, there's a number of problems with this approach. In theory, it should work, but it's all implicit. So you don't copy it to a safe area, you just trust the CPU to keep it in its cache. So if you do this, you can think that if it's implicit putting it in there, then you might also not notice if the cache all of a sudden didn't keep it anymore. So what could go wrong? Well, what if your BIOS is larger than your last level cache? So on a Skylake CPU in my laptop, I think the last level cache is about 12 megabytes. So this shouldn't happen, but it could. Flash chip is 60 megabytes. So if the vendor were to set it up wrong, they think it was protected, but it's not. This is actually what got me on this train of thought at first, because I saw they were using this way, and I thought, well, what if it doesn't fit in the cache? Then I realized cache is large enough, but still wanted to look into it. Because you could also have a cache flush instruction, or maybe something turns the caches off. And then the code would keep running, because it's still at the same address. It'd just not be running from cache anymore, but instead it would be running directly from the flash chip, which of course is a bad idea. So yeah, when I realized this could happen, I decided to hook up a logic analyzer, and this was made possible by my hackerspace, because this is a pretty fast logic analyzer that I wouldn't have access to otherwise. And I captured the trace of the SPI bus, and then I had to write a SIGROC decoder to actually process it, because it's not really just SPI, there's all kinds of optimizations going on. So when that was done, running it took a long time as well, because I think I captured about 4 gigabytes of trace data for a single boot. So of course it's all still serial form. When I'd processed the data, I had a nice log saying which addresses were accessed in which order. And I think a good way to visualize this is just to plot it against time. So all the blue lines on here, blue dots, are the first time an address is read, and everything that's in red is something that's being read again that was already read before. So those are potentially vulnerable. So this is the actual hash of the BIOS being calculated, which is also the point it should be loaded in cache and be safe. Then at some point you start seeing these very frequent rereads from flash, and there's actually a few happening before that. But I didn't really look into those because I just wanted to see if I could easily exploit this, and I didn't really feel like chasing down whether a data read was possible to use to get control of the thing. They probably are. So this is the first one that I could find that would actually directly execute code. So it's this one. That's in the SecCore module. So for those of you who aren't familiar with exactly how UEFI works, this module just sets up the system and isn't really supposed to run very much later in boot. So why is it running here? This is actually this function, the PEI temporary RAM down, which is a handler that's installed by SecCore as a callback to be run after the actual main memory is initialized and when it can clean up what they call temporary RAM, which is cache's RAM. So looking at those addresses in my disassembler, I saw these instructions. So this doesn't look too suspect at first if you're not familiar with the way Intel's cache setup works. It's just clearing a bit in some MSR, model-specific register. But then you get out your Intel architecture manual. You see this is the MTR enable-disable bit. And that when it's set, the MTRs work and everything is fine, but when you clear it, all of a sudden, all of your memory is considered to be uncached memory type. So your caches are effectively disabled, which explains why after this point you start seeing the firmware running execute in place from flash, which it should never be doing. So just to summarize what the actual flow is, that the system goes through while booting. You've got your ACM running, which is a piece of Intel code that's signed by Intel. You can't change it. That verifies the hash on the ROM. That then starts the SecCore, which loads the PEI core, the next stage. And then the PEI core loads the RAM and chipset initialization module, which then goes on to initialize the DRAM and disables cache's RAM before running the rest of the UEFI modules from RAM. But this is how it should work, because actually we just saw that disable cache's RAM step halfway through would disable caches and execute in place from flash. So when I saw this, I thought, well, I need to check whether I can actually use this to run my own code this early at boot. Because the reason that would be useful, of course, is that at this point, almost none of the MSRs have been locked down. There's no system management mode running yet, so in theory you could load all kinds of nasty bootkits, lock it down, and the rest of the firmware wouldn't really notice. So it's pretty bad to be able to do this. So yeah, I set out to try it. So I opened up my laptop. And at first I actually was trying to do this just using clamps, but then I tore off some pads and I decided I needed to do something more safe for my hardware. So I soldered on a header to the SPI bus up here and actually lifted the pad for the chip select pin. So that's running through the header now instead of directly onto the motherboard. Which means that if I bridge that, it's working as normal, but I can interrupt it and have any other device respond to the request being sent by the chipset. And then I made a quick FPGA design that would listen for all the read transactions on the SPI bus, and once it detected an address that I could see in my log would only be accessed after the verification. So in this case, that was one of the EFI variables, which are not included in hash. I would turn on my device, which would then reroute chip select to an external ROM. Now, this is a pretty simple way of doing it, and it's got a lot of flaws because you need to reflash that external ROM every time I want to try a new payload, and it's pretty difficult to time it correctly. So it worked. I was able to run my own code because there's not really a lot of input-output devices available at this point. I decided to use the SPI bus itself to communicate from my payload. So I just had a big area of memory where I would read indexed based on the data, and then could just use that as a simple text mode output. And I wrote a small script that would parse the logic analyzer output, and that would show me what I printed. So just hello world. Later on I did do some more complicated stuff, but I could run code on a machine that had BootGuard enabled very early during boot. So this is set up. Here's the board that has the ROM on it. It's actually not on here at the time I took this photo, but this is the FPGA. And also had the address lines for the ROM decoded and sent out to the logic analyzer, so I didn't have to do the very slow analysis of the SPI trace. I could just look at a parallel bus that showed the address. So this worked. But then I wasn't really sure what to do about it, because I thought, well, it's a hardware attack. Well, who's gonna be interested in that? And this was late December. So I just thought, well, let's get back to it later on. I went to Chaos Communication Congress, and when I was there was this open source firmware booth. So I walked up there and asked, is there anyone here that knows more about BootGuard? And they pointed me to Trammell, and when I said to Trammell, I might have something, I didn't really tell him that much. First thing he does is he opens his laptop and he pulls up this. So apparently, a couple of months before I was doing this, he'd already traced the access pattern and realized that there was probably something fishy going on here, but he didn't really have time to look at it any further. Sent it to Intel, and they said, well, you need to have a proof of concept at first. So yeah, that's what I had. So he agreed to meet up at my hackerspace, RevSpace, and build a better proof of concept. So this time we took it from a big setup with multiple parts to just attaching this FPGA dev board to the motherboard. And yeah, we also switched from having a separate external ROM to emulating ROM when we're overriding it in the FPGA. And there's also now a serial output core in the FPGA that will send you the access pattern as easily readable text over a USB serial port. So no logic analyzers, no expensive tooling required anymore. You just hook this up and you can do your trace and you can attack it. And then there was also something else that needed to be demonstrated. I could run code, but that wouldn't really show that it could go undetected. So we needed to get the system to boot afterwards. In order to do that, we improved upon the basic idea of the time of check, time of use by also adding a second trigger address that, once it's read, will disable the entire device, make it invisible again to the system. So at the end of our payload, we then read that address and jump back to the original instruction that was supposed to be executing after it. And that way, the system would boot as normal, and once it booted up, the PCR, so the measurement registers and the TPM would show no sign of tampering. So this is pretty bad. It meant we could run whatever code we wanted early at boot, and the system, the TPM, wouldn't notice. So at this point, Trammell contacted some people at Intel. We sent them an email, also containing this nice video we made. It's so it's not really that interesting, but a simple payload beeping out my radio call sign in Morse code just to show that we can actually run code. Because one of the only output devices working is the speaker at this point. And it takes a while, and my laptop's crappy, so it will reboot after this. So it'll do it again, and then it'll continue booting. So that pretty much proves that we're running code at a point that we should not be, and we still have a functioning system. So Intel responded, I think, within a working day, and they said, yeah, that's not supposed to be happening, and we're going to fix it. So they were really responsive in that, and I do want to really point out that even for something as difficult to exploit as a hardware attack, Intel was very responsive, and they immediately acknowledged that it was actually a security issue. And they actually assigned a pretty high severity to it, so yeah, that was really nice working with them on that. Let's see. So this still required modification of the hardware. So to interrupt that chip select line, which means that you need to be soldering on your machine. It's actually pretty small. So yeah, you need a lot more than just somebody opening up a case, plugging something in, and leaving again. So still not really practical. This is actually what we were doing, interrupting chip select and just branching the other ones out to the FPGA. But then we realized that most motherboards allow just connecting a programmer in parallel to the flash chip without removing it. And in order to prevent damaging the chipset by having two drivers on the bus, there's some series resistors in there on, amongst other things, the chip select line. Which means that you don't actually need to interrupt it. This will work just as well. You've got the series resistor, and then you can just use an input-output pin on your FPGA and drive it strong enough to pull it down. And that way, it becomes a lot more simple. So all of a sudden, you don't need to modify it anymore, and because we moved everything to the small, cheap FPGA boot board, you also don't need a big, expensive logic analyzer. So this is actually Trammell setup, and as you can see, it's just a SOIC clip and a small dev board. And then for debugging purposes, there's this oscilloscope, but this is, I think, what, 20, 30 euros worth of hardware at most. So all of a sudden, it's something that everyone can do, that everyone can build. You don't need a lab, you don't need to solder anything. So yeah, it becomes a lot more practical of an attack all of a sudden. So let's see. And this isn't just restricted to Intel systems. There's a lot of other devices which uses SPI flash. So using this tool, we could just hook it up to any device and see whether it was doing repeated reads and try to attack those. In fact, Trammell looked at a board management controller before, which he also discussed in his talk at Chaos Communication Congress this year, to see if he could attack that in this way. That turns out to be possible. It's also possible for a lot of different systems. And you can maybe see on here that there's this ROM chip sitting out on some kind of a breakout board. This is actually a stock part of the hardware. We were also able to come up with a design containing the FPGA and the ROM chip that's small enough to fit in this form factor to just be soldered in place of a normal SOIC chip. So all of a sudden it's not just something you can clip onto a motherboard, but that you could actually put in there during production and have a system that looks normal, that when you run flash ROM it will seem fine, give the right results, but actually contains malicious code. So it's also something that could potentially be used as part of a supply chain attack, which is actually what Trammell's talk at CCC was about, where he discussed the feasibility of what Bloomberg was claiming, the whole small passive component being replaced by a by an implant thing. Actually discovered that to be not that unrealistic. So now I'll hand this off to Trammell to discuss the mitigations that Intel's planning against this.
Thanks, Peter. So as Peter mentioned, Intel responded very promptly to our vulnerability report. It's been 125 days since then, and they are working on getting patches into the OEM and IBV supply chain. As I pointed out in a lot of my firmware talks, one of the big problems is it takes a really long time for firmware patches to make it all the way out to the end user. Because typically, Intel fixes it in their reference code. The independent BIOS vendors pick up that patch and apply it to their new systems, but they may not backport it to all of their old systems. But it is really encouraging that Intel is taking these sorts of hardware vulnerabilities seriously. They are creating high severity bugs for them, and they are actively patching them. The fix that they have proposed to this one is really quite comprehensive. I'm really pleased with what they've proposed to do, which is that they are going to relocate the entire contents of the firmware volumes from the flash ROM into RAM. And then they're going to fix up any addresses and relocate any executables in that region. Then they're going to flag the ROM regions as being no read, no execute, so that they can ensure that there are no TOCTOU attacks possible from the SPY flash chip. This is a really good way to deal with the entire class of attacks, and I'm hoping that all of the independent BIOS vendors and the OEMs pick up these patches from Intel and very quickly get them into their supply chain so that they can protect their systems from these sorts of attacks. The other way I think that we as a community need to be addressing a lot of these attacks is by moving to more open source firmware, that we shouldn't have to be reverse engineering these things. As Jess Frizzell pointed out in her recent 44Con talk, we need to be building firmware that we can inspect, that we can audit, that's reproducibly built, that we can measure into trusted devices, so that we as system owners can actually have some assurance that what is running on the machine is what we built and flashed onto it. So the Core Boot project, the Linux Boot project, and the Heads project are three fairly mature projects that are addressing this, and Jess talks about them in her talk. It's worth watching. Peter and I will also be releasing the Verilog code for our SPY device that will allow other researchers to experiment with our own machines. As Peter mentioned, pretty much every machine we've looked at so far has had potentially exploitable TOCTOU on the SPY bus. So having a 10 or 20 euro device to be able to investigate this will hopefully get the industry to move towards fixing these problems. We're currently working with Intel on the disclosure timeline for releasing the source code, but hopefully that will be sometime in the next month or so. So with that, would love to take any questions that you all might have about BootGuard, about spy buses, about TOCTOU, about all of these sort of deep hardware security things. And thank you all for coming out to listen to our talk.
Yes, thank you so much for your presentation. Are there any questions? Yes.
Hi, I have a question. Is it possible to use the same technique, for example, to hack into a hard drive firmware rather than ROM?
So most of the hard drives are running ARM or RISC-V CPUs. Many of them have on-die boot flashes. However, a lot of the OEM code is not particularly high quality, so I expect it would work for many hard disks. We've certainly seen it works against ARM-based BMCs, so we expect that we could extend it to many other ARM devices.
Hi, thanks for the talk. My question is, from a systems owner perspective, is there any way they can detect this at this moment? Are there any tools to see that malicious code has been loaded, or how can they go about that?
Well, that's a yes and a no, because in terms of this having happened to your system, at the moment you can't see it from a software side because the code hides itself again after being run. And if someone would have made the device that I described that would fit inside the footprint of one of these chips and camouflage it as a chip and install it in your machine at some point, I think nothing short of an X-ray of the machine would really point that out. But on the other hand, you can at least detect your system being vulnerable, even if it's already being exploited by using this device and looking for the access patterns. So you can just hook it up, it'll throw some numbers at you through the serial port, you plot those. And then if there's a lot of red in there, then there's a good chance that your system is vulnerable. It's actually that simple.
And if anyone wants to get together afterwards, and we can pop open your laptop and give an in-person examination. Can't promise we won't leave anything else in there, but you might have to trust us on that.
Any other questions, guys? All right, if that's it, then thank you, Trammell and Pedro.
Thank you.